The next lessons examine two threats that a polished regression table can hide. The classical regression model assumes that the conditional variance of the error is constant across observations. Heteroskedasticity means that this variance changes with one or more regressors. The conditional mean may still be correctly specified, yet the cloud of outcomes can be narrow for some observations and wide for others. This pattern is common in cross-sectional economics. Larger firms can have more variable profits than smaller firms. Higher income households can display a wider range of expenditure. Countries of different sizes may have very different shock magnitudes. Heteroskedasticity can also signal an omitted variable, an inappropriate functional form, or a structural change. Under zero conditional mean, heteroskedasticity does not by itself bias the OLS coefficient estimates. They remain unbiased and consistent under the usual regularity conditions. The problem is precision. OLS is no longer guaranteed to be the most efficient, linear, unbiased estimator, and the conventional homoskedastic standard error formula is generally incorrect. Incorrect standard errors contaminate confidence intervals, t-tests, and f-tests. If the conventional formula understates uncertainty, we may declare effects significant too often. If it overstates uncertainty, we may overlook useful evidence. The direction is not known in advance, so the fact that coefficients appear plausible is not a defense against a variance problem. In simple regression, the heteroskedastic variance of the slope depends on a weighted sum of observation-specific error variances. Observations whose x values are far from the sample mean receive greater leverage in that expression. If those influential observations also have high error variance, the slope can be much less precise than the homoskedastic formula suggests. The intercept variance changes as well. Formal tests begin with the OLS residuals from the original mean model. Many then use squared residuals as proxies for unobserved error variances. An auxiliary regression asks whether those squared residuals are systematically related to selected variance drivers. Its convenient sample size times R squared form is an asymptotic result. In a small sample, the approximation and the sensitivity to unusual observations deserve caution. The White test uses a more flexible auxiliary regression. With two original regressors, it can include those regressors, their squares, and their cross product. Curvature omitted from the mean can create a patterned residual spread and trigger heteroskedasticity tests. Before selecting a correction, ask whether the residual plot suggests changing variance, missing non-linearity, omitted groups, or several problems at once. It is also unnecessary to earn permission for robust standard errors through a preliminary rejection. A pretest can add instability because the final method changes according to a noisy p-value. When heteroskedasticity is plausible, reporting a suitable robust covariance estimate alongside transparent diagnostics is often a sensible default. Sample size changes how we read the evidence. In a small sample, a visually suggestive pattern may not produce a small p-value, while a very large sample may reject a mild and economically unimportant departure. We should describe the pattern's magnitude and practical consequence, not only whether a test crosses a conventional threshold, so no single test settles this on its own. What I want you to take away is that a good analysis combines residual plots, economic reasoning, and tests aimed at the patterns you actually expect, and keep detection separate from correction. When we reject constant variance, that tells us our usual standard errors need attention, but it does not tell us which weighted model is the right one. That is exactly the question we take up in the next lesson. Once heteroskedasticity is credible, we face two separate questions. How should we conduct inference, and can we estimate the coefficients more efficiently? Robust standard errors answer the first question while keeping the OLS coefficients. Generalized least squares addresses the second by weighting observations according to a variance model. White's heteroskedasticity, consistent covariance estimator, replaces unknown observation-specific error variances with functions of squared OLS residuals. In matrix language, the estimator has a sandwich form. The outer pieces reflect the regressor geometry, while the middle piece lets residual variation differ across observations. Several finite sample versions are labeled HC0 through HC3 and beyond. Here, HC stands for heteroskedasticity consistent. These versions share the same large sample objective, but adjust residual contributions differently. HC1 applies a degrees of freedom correction. HC2 and HC3 account more directly for leverage, with HC3 often used as a cautious choice in smaller samples. Robust standard errors leave fitted values, residuals, and coefficient estimates unchanged. They change the estimated uncertainty around those coefficients. A robust t-statistic divides a coefficient estimate by its robust standard error.